Hello again, guys. Today what we're going to talk about for AP Chem is we want to talk about empirical formulas. We want to figure out how to determine an empirical formula. We also want to see how can I use an empirical formula to determine a molecular formula. So this is all about figuring out chemical formulas today. So I want to start off with defining what an empirical formula is. An empirical formula is essentially just the simplest whole number ratio between elements in a compound. So if I were to look at a molecular formula for a molecule, we'll choose a simple one like glucose. All right, C6H12O6. Would you say that this is the simplest whole number ratio between these elements? The fact is, I can reduce every one of these by a factor of 6. And so this would not be an empirical formula. This would be a molecular formula. If I wanted an empirical formula for this, I do just that. I reduce it by whatever factor I can. And so I can see the ratio here is for every one carbon or oxygen, I'm going to get 2 hydrogens. So my empirical formula for this would simply just be CH2O. All right, so basically if I multiply all of these by 6, I get this formula. All right, the empirical, though, is 1 to 2 to 1. This same empirical formula, though, would also work if I did C4H8O4. That has the exact same empirical formula. All right, it's still 1 to 2 to 1. All right, so I can have a multitude of molecular formulas that all have the same empirical. Now, here's why empirical is important. If I go to test, let's say I have an unknown substance that someone brings me. If I go to test that substance to see what its formula is, I really have no way of knowing what these are. I'm going to end up with if I measure the mass of each one of these elements that make up this compound, I'm going to get a whole bunch of carbon and twice a whole bunch of hydrogen and a whole bunch of oxygen. So I'm going to get this ratio. That's what I'm going to see when I test it. So getting empirical formulas are usually what you're going to get when you figure out a compound's formula. You got to do a little trick to figure out what molecular is, but we'll get to that in a few minutes. So again, empirical formulas, simply the simplest whole number ratio between the elements. Okay? Let's talk about how you're going to determine an empirical formula by looking at a few examples. So we're going to go ahead and put an example on the board over here. I have it actually in my book, and it tells us to determine the empirical and molecular formulas for a compound that gives us the following mass percentages. And it tells us that the mass percentages that we have are 71.65% chlorine. It tells us that we also know we have 24.27% carbon and 4.07% hydrogen. So I'm going to kind of list some steps over here. Get out of the way of this question. Hopefully I'll be a little bit lower. I'm going to put a series of steps up here to kind of describe for you the way that you're going to get an empirical formula when it asks you for one. So the first thing you need to do to determine an empirical formula is you need, number one, to figure out or realize that there are only certain elements here, and we know the percentages of each. The problem is that when I write this compound's name, this formula, I should say, it's going to look something like this. It's going to look something like that, where X, Y, and Z are going to be the simplest whole number ratio between those three different elements. Now you might ask, well, why'd you put chlorine last? Why is carbon first? The way that we usually do this is compounds are normally written so that the most electronegative element is the last one, is the furthest right. Chlorine has a higher electronegativity than either carbon or hydrogen. The other one that we do is, that would mean we put the least electronegative first, and sometimes that would be hydrogen, but when we have hydrocarbons, meaning something with hydrogen and carbon, we never put the hydrogen in the front. The carbon goes in the front, okay? So it'll go carbon, hydrogen, and then if you're dealing with a very electronegative element like chlorine, it goes last. So our chore is to figure out here X, Y, and Z. What are those numbers going to be? So when we start in the steps, the whole idea is to get those ratios. Well, those ratios are between moles. For every 1 mole of this compound, I have a certain number of moles of carbon, a certain number of moles of hydrogen, and a certain number of moles of chlorine. So I really need mole ratios. So if we're given a percentage like this, the very first thing you do, assume that you have 100 grams of the substance. Now, why would I do this? Because that makes these percentages turn into grams really easy. If I have 100 grams of this substance, how many grams of chlorine would you have? Well, if you have 100 grams of it, you'd have 71.65 grams of chlorine. Okay? So if I have 100 grams of this stuff, every one of these percentages just turns into grams. So if I have 100 grams of the whole thing, I'm going to have 24.27 grams of carbon, and I'm going to have 4.07 grams of hydrogen. Okay? So assuming that you have 100 grams of a substance allows me to change those percentages into these masses. Now remember, I told you guys that X, Y, and Z are mole ratios, not mass ratios. So what do you think the next step's going to be if I know the number of grams of each substance that I have, but I know I need to have these in moles to make mole ratios? Well, I need to convert. I need to convert from grams to moles. Okay? This is a pretty straightforward conversion that you guys have already done this year. If I want to go from grams of chlorine to moles of chlorine, I need to use molar mass. Grams Cl, moles Cl. For every 1 mole of chlorine from the periodic table, we know that's 35.5 grams of chlorine. I don't know why I do this, but I always do this step at the same time for all of them. So I know I'm going to need moles of carbon. I know I'm going to need moles of hydrogen. I guess I'm just kind of in the mode to convert when I'm doing this, and so that's the way that it goes. If I look at molar mass of carbon, grams carbon, moles carbon, again with molar mass that we're using here, the mole term's always 1. There's 12 grams of carbon in 1 mole of carbon from the periodic table. For 1 mole of hydrogen, there's 1 gram of hydrogen, again from the periodic table. What you'll notice with units, these guys all cancel. The grams of carbon, the grams of chlorine, the grams of hydrogen all cancel. And for every one of these little calculations, I'm left with moles. All right? So remember, these are mole ratios, so we have to get these into moles. I'm going to go ahead and get my calculator up here, and we will figure out what these are. 71.65 divided by 35.5. I get I would caution you when you do these, don't round these numbers too much. Okay, you can do rounding at the end. Right now, I want to keep these with a fair number of digits. I usually use at least 4 sig figs in this. So I had 2.0183. I'll just go ahead and use all of them for right now. All right, I'm going to do the same thing here. I can see already this is going to be a number right about 2 also. So this is 24.27 divided by 12. And I get 2.0225. 2.0225. Okay? And this is a real toughie. 4.07. Now, some of you guys, if your brain's kind of trained to look for patterns, you may already see what the ratio is going to be here. But to kind of make this official, we're going to go back over here to step 3. You're going to divide all the moles by the smallest. Number of moles. All right. So why am I doing that? Why am I going to divide all 3 of these by the smallest number that I have? Well, remember, I told you X, Y, and Z, yes, they're moles, but they're a ratio of the moles. All right, so I'm basically getting a ratio between all of these. Why am I dividing? Because that's how we get ratios. So if I look at all 3 of these, I can see that this one here is the smallest. So I'm going to divide all of them. Should have given myself more room. By that number. This is easy. That's 1. Okay? Now, this one here. You can see this number is not exactly 1, but it's really close. So 2.0225 divided by 2.0183. Yeah, the number I get when I do that is 1.0020. Now, you might say, well, why is it not exactly? Why is it not exactly 1? Remember, the name of this type of formula that we're doing is empirical formula. An empirical formula, empirical means you tested it. You did an experiment to get these values that are here. All right, so is any experiment always going to be 100% without error? No. I will tell you that every experiment you do has some amount of error. So it makes sense that when you do these ratios, they're not going to be exact. But you can see that if I get 1.002, I am close enough to 1 that I can be pretty confident. I can be pretty confident that this number is 1. This ratio between chlorine and carbon is essentially 1 to 1. All right, so I'm going to say that's approximately 1. You guys who are watching and paying attention to this probably already know what the answer for this is going to be. 4.07 divided by 2.0183. I get 2.0165. Again, I am going to say that that is close enough in the experimental realm that that's going to be a 2. All right? Now, I already know what you're going to ask, I think. If you're really paying attention to this, whenever you say, okay, it's approximately 2, where's the cutoff? When is it okay to round, and when is that difference just too big to round? My rule of thumb is, let's just say that I came out with a number that I'm going to round to 1. I usually go about 0.05. So anything that I see that's between here and here, I'm usually feeling pretty good about rounding that to 1. All right. But this is one of the reasons why I told you guys a few minutes ago, don't round too much before you get to the end. Because if you do a lot of rounding here, you're going to get these numbers that will make it much more difficult to see if they need to be rounded or not. Okay? I will tell you, there's a couple of fractions that you know you can't round. So for instance, if I came out with 2.5 for this, or 2.25, or 2.33, if you think about it, if you have half, that would mean maybe this is a 2, and a 5 if it was 2.5 here. Okay? We'll get into that later. But for now, this is going to allow me to write the empirical formula for this. The empirical formula for this compound, CH2Cl1. All right? This is our empirical formula for this particular compound. Okay? So again, on step 3, we said you're going to divide all the moles by the smallest number of moles. That's what we did to get these numbers. And what I would say is that those numbers are typically, that you come out with here, are typically going to be the subscripts for your empirical formula. I want to get out of the way of the problem. All right? That's how you do empirical. Now, what I'm going to do right now, really quickly, because the question asks to get the molecular formula also. Okay, so how am I going to figure out the molecular if I know the empirical? Well, remember, this is the simplest ratio between these elements. But when I think about the molecular formula, what it could be that same number, CH2Cl. I messed that up. All right? The empirical and the molecular could be the same thing. But it could also be C2H4Cl2. It could be C3H6Cl3. And I could go on and on and on. But I want you to notice that there is a relationship between this and each of these. If I take the empirical mass, so I'm just going to add up these, get the molar mass of the empirical formula, I would get 12. 2 hydrogens is 2. 1 chlorine is 35.5. If I add those together, I get 37, 47, 49.5. What did I say? 47? 49. 49.5 grams per mole. That's my empirical mass. Now, if I were to calculate the molecular mass here, it would be 49.5. It's the same formula. But what about this one? Well, if this is 12 and there's 2 of them, that's 24. If this is 4 and they're each 1, that'd be 4. And 2 chlorines, if they're each 35.5, that would be, 2 of them would be 71. Okay? If I add all those together, I'm going to get 75 plus 24, that's 99. If I were to do the same thing here, this would be 36. There's 6 of these, because they're 1 each, that'd be 6. And 3 chlorines, oh gee whiz, that would be 71 plus, would be 106.5. If I add those all together, I'm going to get 142, 148.5. Okay. So what I hope that you see, the total mass here was 49.5. Okay? Well, if I multiply 49.5 times 2, I get 99. If I multiply 49.5 times 3, I get 148.5. And so what I'm saying here is in every case to go from empirical to molecular, and I've made a huge mess out of this, I'm going to have a multiplier. There has to be a multiplier that will allow me to convert from empirical into molecular. Our problem is we don't know what the multiplier is. How did I figure out what these multipliers were? Well, you think about it, I took the molecular mass that was given, and I divided it by the empirical. 148 divided by 49.5 is 3. 99 divided by 49.5 is 2. 49.5 divided by 49.5 is 1. We have to figure out the multiplier, and to do it, we're just going to use those two masses. So, how do we get that multiplier? Because, again, what we want to do here is we're going to say empirical formula times your multiplier equals your molecular formula. So again, how do I get the multiplier? Multiplier equals molar, sometimes they'll call it molecular mass divided by empirical mass. I can't write empirical for some reason. Okay, so I just need to figure out what's the molecular mass divided by the empirical mass. Now, our question told us that the molar mass, same thing as molecular, is 98.96. So if I do this, I'm basically saying 98.96 divided by, we already know the empirical mass for our substance is 49.5. And if I do that, (98.96) divided by 49.5. I get 1.999. This number is 2. Okay? That number is 2. So our molecular formula then should be the empirical times 2. So it would be C2H4Cl2. This is our molecular formula. Okay? So on this question, this is how we would get both the empirical formula and the molecular. Let's talk for just a minute about what you might want to be doing when you're watching people go over examples. I know some of you guys probably zone out when you watch a math teacher or your science teacher go over something that's an example out of the book or that kind of thing. But as for me, I learn by watching examples. You could sit there and give me steps all day long. I'm not really so much a step follower as I like to watch what a person does and figure out what the steps are on my own. And then when they're doing another example, I know I have it when I can watch what they're doing and predict what they're going to do next. So ideally, as you watch me go through some of these examples, you want to be saying, okay, what's he going to do next? With what he has, what's he going to do now? Okay? So we're going to look at a second example here. And again, you guys can look at the steps and see if you can figure out what I'm doing next. But this one says, a white powder is analyzed and found to contain 43.64%, 43.64 grams of phosphorus, 56.36 grams of oxygen by mass. And then it says the compound has a molar mass. So I'm just going to put that over here, and I'll just say MM. The molar mass is 283.88. I better write it a little bit further. I'll write it underneath so I don't run out of space. 283.88. Okay, so that's our molar mass. So we have this information is what we have. And what's it asking for? It wants to know empirical and molecular. Empirical and molecular. I'm going to give you about 2 or 3 seconds. What am I going to do right now? If you said to yourself, assume you have 100 grams, you're right. I'm going to assume that I have 100 grams of this. Oops, wait a minute, I don't need to do that. Why don't I? Because it's already in grams. The whole purpose for doing this is to get this into grams. Well, I'm already in grams. So I can go straight to step 2, which is convert your grams into moles. Okay? So we're going to say that we have 43.64 grams phosphorus. We're going to say that we have 56.36 grams oxygen. We want both of these converted into moles. All right. So I need to use molar mass to make these conversions. Grams phosphorus, moles phosphorus, grams oxygen, moles oxygen. I know that the molar mass of oxygen is 16. Each mole of oxygen has a mass of 16 grams. I think phosphorus was 31. Let me double check. Phosphorus is 30.97. So we're going to call this, we'll call this 31. And that's 1 mole. We can go ahead and do the math now. I'm going a little bit faster since we already went over the steps. And where are we at? We're right in the middle of step 2. 43.6 divided by 31 equals, I get 1.406. I can't write. .406. Okay. And the bottom, I get 3.552 or 3.522. 3.5225. Okay. What am I doing next? I'm going to divide by the smallest number of moles. This is what I want to do next. So I can see by looking at the 2, the 1.406 is the number I'm going to divide both of these by. This clearly comes out to 1. If I look at the bottom here, I get I did something wrong. Let me go back and do that. I think my calculator messed me up. 3.5225 divided by 1.406. That's more like it. This number comes out to 2.505. Now, normally at this point, I would be saying, okay, my empirical is P1O 2.5. The problem is I can't have 2.5 of an atom. I can't. I can't take my atomic tweezers and cut off half of an atom and include that here. So here's what you do when these numbers aren't whole numbers. All right? So I guess you could say that after you do this, we could add one more step, which is multiply by a small whole number until you have a whole number ratio. Not ration. Okay. So we have to do that on this one. Now, sometimes it's really easy to see what that number is going to be. All right, I can tell by looking at this. This 2.5, I know if I just multiply both of these by 2, I'll have a 2 to approximately 5 ratio. See, when I see a 2.5, I know what this multiplier is going to be. If I see a 2.25, I know that that ratio is going to be a 4. I have to multiply both by 4. If it was 2.33, I know I'm going to have to multiply both of them by 3. So when those ratios come out really close to a third or a half or a quarter, figuring out what this multiplier is going to be right here is easy. So what is our actual ratio here for our empirical formula? Our ratio is going to be P2O5. That is our empirical formula. Okay? What about molecular? Well, let's figure out what the mass of the empirical is first. This is 31, and there's 2 of them, so that would be 62. This is 16, and there's 5. That would be 50 plus 30. That would be 80. Okay? So I know that my empirical mass must be 142. All right? Okay. I know that my empirical mass is right around 142. I need to get the multiplier. So just like the last question, your multiplier is simply going to be equal to your molar mass over your empirical mass, or 283.88 divided by, I'm going to move off screen, divided by 142. Now, I can tell just by looking at this, if I doubled 142, I get 284. So this has to be, my multiplier has to be a 2 here. So what would that mean about my molecular formula? Well, I'd have to take the empirical times 2. So it would be P4O10. Okay? That right there is my molecular formula for this particular question.